All right, how is everyone doing today? Hope everyone is having a good day so far. And today we'll mainly be talking about inductors and I guess really cool circuit called the LC tank. So just to give a recap from last week on what we've done so far, we've taken a look at how to solve vector differential equations of the form dx dt is equal to ax, where x is a vector. And in order to solve these, we use something called diagonalization in order to write our final solution as a linear combination of all of these eigenfunctions, e to the lambda I t, where lambda I were the eigenvalues of A. And then on Monday, this discussion, we took a look at complex numbers, and I'm not sure if the motivation was 100% clear there, but the real motivation behind complex numbers are to model rotations and oscillations that occur in the real world. So even though something's occurring in the real world, that's like a rotation or an oscillation, complex numbers are a very helpful tool to help us understand what those actually mean. And so the brief overview for what we're going to talk about today, we're going to take a look at an inductor, and we're really going to see how it behaves when paired with a capacitor. So just a bit of, I guess, overview for what's to come. You might have seen in lecture, or you might know that the voltage across an inductor, VL, is equal to L di dt. Whereas for a capacitor, remember that IC, or the current across a capacitor, is equal to C dV dt. So really the two devices, the inductor and the capacitor, behave opposite to each other. In other words, the roles of V and I here are switched. And this really is one of the key ideas behind the LC tank, which we'll see later in this discussion, in which the LC tank has complex eigenvalues. And the complex eigenvalues, again, are what create these oscillations in the LC tank. So we'll take a look at that later today, and we'll see how the energy in the LC tank oscillates from one side to the other. So any questions about what's happened in the past or what's to come today? All right, if we don't have any questions, let's actually talk about what an inductor is and a little bit about, I guess, some of the physical intuition behind an inductor. So inductors, they're just another electrical device, just like a capacitor or resistor. And inductors are very, I guess, cool or different from the other devices in that they store something called magnetic flux. And flux is kind of an abstract concept. So if you look at an inductor in real life, you'll see how it's like a 3D coil. And when current flows through this coil, as you'll kind of see through these like coils here, a magnetic field is going to flow through the entire coil. So like in 3 dimensions. So we had like a circle. It's going to flow through the circle. And that amount of flow is called flux. So the blue lines over here all represent the magnetic flux that flows through an inductor. And for notation's sake, we often use the Greek letter phi to denote the actual flux that flows through an inductor. And you can think of flux as the analog for charge in an inductor or for magnetic field. So similar to how the charge stored in the capacitor is equal to C times V, or the capacitance times the voltage for a capacitor, you can say that the flux that flows through an inductor is equal to the current times the inductance, or L times I. So, any questions about the way flux works or these like capacitor inductor voltage current relationships? Okay, if we don't have any other questions, let's take a look at the IV relations for an inductor. So for all of these devices, resistors, inductors, and capacitors, you always want to kind of figure out what the current voltage relationships are, because it's going to help us put what's going on physically in the circuit into mathematical equations. So from the previous slide, we saw that phi is equal to Li, or the flux, the magnetic flux, is equal to the current times the inductance. And if you've taken physics, you might actually know something called Faraday's law, which tells us that the instantaneous rate of change in flux, so d phi dt, is equal to the voltage. In other words, this inductor is generating this voltage difference based on the instantaneous rate of change of flux. Similar to how the capacitor generates a current based on the instantaneous rate of change in voltage. So if we look at these mathematical equations, we can take the derivative of the first equation with respect to t to get d phi dt, which is equal to the voltage, is going to be equal to L di dt, since L is a constant. So we can therefore conclude that the voltage across the inductor is equal to L di dt. So any questions about how we derive this idea that V is equal to L di dt? Okay, and the last thing I wanted to say was that if you might remember that capacitors behave like open circuits at steady state. In other words, if we put a voltage across a capacitor, wait a really, really long time, you might remember how at steady state it behaves like an open circuit. Inductors, however, on the other hand, behave like shorts at steady state. And you can kind of see this since VL is equal to di dt. And when the current stops changing, in other words, when di dt is equal to 0, you'll notice that VL is equal to 0. So an inductor will have no voltage difference across it at steady state, meaning it behaves like a short circuit. And just to give an example here, we had a circuit with a resistor, an inductor, and a capacitor, and we took it at steady state. The inductor behaves like a wire or a short. The capacitor behaves like an open circuit. So no current is going to flow through the capacitor. All of it's going to flow through the resistor. So we can reduce the circuit to a simple circuit with two resistors. So any questions about inductors as a whole? Why is the capacitor bent? I think, yeah, it's like a technicality where like, I just took the like image from like Google Images, but like it's like a polarized capacitor. And if you're curious about what a polarized capacitor is, like feel free to just like Google it. It's like there's like a small distinction between like a polarized capacitor versus a normal capacitor. But yeah, it's a good question. Why is it bent? And, like, I think for all practical purposes, though, it doesn't make a difference in terms of the equations and math. All right. If you don't have any other questions, let's move on. And we're going to mainly look at the discussion worksheet today. And I think the main idea is here in the first question, at least. So we talked about the note. Let's see, we mainly talked about the note or everything in the first page in the slides. And now we want to take a look at what happens when we put inductors in series or inductors in parallel. So the first question, part A, asks, what is the equivalent inductance for two inductors in parallel? So if we had two inductors in parallel, we can actually replace it with a single inductor. And we want to find what this inductance is. So give everyone around a minute to work on this. And in the meantime, feel free to ask any other questions you have as well.
How does the property of inductors change with lengths and area? Like, you know how for capacitors?
Yeah, that's a good question. Perhaps I should write that on the slides here. I forget the exact formula. It's like, let me Google this real quick. Something like mu NA over I or something. Like inductor formula. Inductors are quite an interesting device because the number of turns and the area have a huge effect on the actual inductance. And if I can actually pull up the formula from somewhere. It's mu n. Is it actually mu n A over? Google doesn't seem to be helping me out here. It's n squared mu times A over I. And so n here is the number of turns. So like physically, how many times is this inductor like turning? A is the cross-sectional area. And then, actually this is not an I, this is an L. And L is the length of the inductor. So hopefully that helps answer the question. And mu is again just another constant, which represents like magnetic permeability. I think it's like similar because like for a capacitor, you might remember the capacitance is equal to like epsilon naught A over D, something like that. Where epsilon naught is again another permittivity constant. Okay, let's take a look at the first question. So I think the key idea here to solving this is to understand what happens in a circuit when a device is in parallel or in series. So in parallel, the voltages are the same. So the voltage across the first inductor and the second inductor are the same. And then the currents branch off. Due to KCL. And what I mean by this is if we were to have currents I1 and I2 going through the inductors, like I equivalent is equal to I1 plus I2. So first thing we should do is to write out our KCL equation. I equivalent is equal to I1 plus I2. And then I think I'm just going to take the derivative. And I'm going to take the derivative because we know V is equal to L di dt. And this is going to help us simplify our equations. And then remember our original goal. Our original goal was to create a equivalent circuit with a single inductor and a single voltage difference, like V plus V minus. So from here, what we can do is we can substitute di dt as V over L. In other words, di equivalent dt is going to be equal to V equivalent over L equivalent, where L equivalent is our unknown. And then we have two inductors here, each of which have voltage difference, V1 over L1 and V2 over L2. But again, since they're in parallel, we know that V1 equals V2 equals V equivalent. So we can just substitute these in. And if we divide through by V equivalent, this tells us that 1 over the equivalent inductance is 1 over L1 plus 1 over L2. So it behaves very similar to resistors, where L equivalent is just the reciprocal of the inductance, or reciprocal of the parallel like sum. So I think you can simplify this as the parallel operator, just like how we do for resistors. So any questions about how we were able to take two inductors in parallel and solve for the equivalent inductance? All right, so I'm not going to spend too much time on the second part. The second part asks, what happens if we have three inductors in series? So I guess if two inductors in parallel behave the same way as two resistors in parallel, any conjectures on what would happen if we had like three inductors in series? How do y'all think it'll behave?
You just add them up.
Yeah, so it'll behave the same way as three resistors in series. So you just add up the inductances. And you can like formally show this. And the key idea here is again to know that in series, the currents are the same. And then the voltages sum up by KVL. So in other words, summing these three voltages is the same as V equivalent by KVL, and all of these currents are the same through KCL. So I think you can do that on your own time. And let's move on to the main topic of today, which is the LC tank. So the LC tank is just the circuit that I've been talking about without actually giving an actual visual to, of an inductor and a capacitor in parallel. So these two are in parallel. And what we're going to see is we're going to see that the charge on this inductor is going to like move to the capacitor, or sorry, charge on the capacitor is going to move to the inductor as flux. And then once like the inductor starts becoming like charged with magnetic flux, it will go back to the capacitor. So they'll keep going back and forth. And we can use math to show why that is the case. So we have the actual setup of the problem. We have this LC tank where we have two devices in parallel. And the first part is to write out a system of diffie Qs. So give some time for y'all to think about this. And if you have any questions in the meantime, feel free to ask as well. All right, so let's take a look at the problem now. Any ideas on how we should start? If you have any ideas, type in the chat.
IC equals negative IL.
Was that IC equals minus IL?
Yeah, for KCL.
Yeah, KCL tells us IC equals minus IL. That's good. And whenever the question asks you to set up a system of differential equations, the first thing I like to do is I like to take a derivative of the states. So let's just take dx1 dt and dx2 dt. And the reason I do this is because we want something of the form dx dt is equal to ax. So might as well figure out what dx dt is first. So we take the derivative of IL. And we take the derivative of VC. And what do we get? Well, we know that for a capacitor, we know that IC is equal to C dV dt. And for an inductor, we know that VL is equal to L di dt. So given di dt, we know that it's equal to VL over L. And given dV dt, that's equal to IC over C. And then we use KCL, as someone earlier mentioned. And we can also use KVL to say the voltage here is equal to the voltage here. So VC is equal to VL. So we can write VL over L as VC over L. And the reason I'm doing this is so that we can write everything in terms of our states, VC and IL. Since right now we had VL and IC, which aren't actually the states. So cleaning everything up, we get something like dx1 dt is equal to x2 over L. And dx2 dt is equal to IL over C. So then that's x1 over C. So minus x1 over C. And to put it all into a matrix, we can actually see that it's equal to like 0, 1 over L, minus 1 over C, and 0. So, any questions about the whole process? Okay, so moving on. In the next part, we can notice that if we're to take the equation for an inductor, so we showed here that dIL dt was equal to VC over L. And If we take one more derivative, we can actually show that this is equal to 1 over L dvc dt, which is then just equal to like 1 over LC IC over this, 1 over LIC, which is then equal to negative 1 over LCIL. So we have the second order differential equations. And this specific type of second order differential equation is called a simple harmonic oscillator. And someone back in the day proved that the solution to a simple harmonic oscillator is of the form like cosine and sine. So the idea here is that we're going to guess and check a sine or a cosine instead of doing the whole diagonalization approach. Like, we're going to come back to diagonalization at the end just to like rigorously prove why it is the way it is, but for now we're just going to guess and check just to get an idea of what our solution should look like. So any questions about the approach so far? Someone in the earlier discussion asked like what a simple harmonic oscillator was, so I wanted to make sure that was clear. Okay, so I'm gonna give everyone some time to work on this. Perhaps we should try using some breakout rooms. And I think the main idea here, so what we want to do is we want to guess and check. So what we want to do is guess and check VC is equal to A cosine of omega t plus theta, and solve for everything. So solve for A, omega, and theta. And I think the hint I'm going to give you is to use all information you have, including the initial conditions. VC of 0 is equal to 1, and IL of 0 is equal to 0. So use all the information you have. All right, so let's take around 5 minutes to work this out. And it is a bit challenging, so don't worry if you get stuck on it. Okay, as people are coming back, anyone have any ideas for how to start?
Take the first and second derivatives of your guess.
Yeah, let's take the first and second derivative, I guess. So we have VC is equal to A cosine of omega t plus theta. And let's take the derivative. And you might remember from calculus that the derivative of cosine is negative sine. And then you also need to use the chain rule. So
Sub them back again.
this is the first derivative, and then let's take the second derivative. And the derivative of sine is cosine. So you'll notice that after taking two derivatives, you get the same cosine back. So let's plug this in to the differential equation. So we get negative a omega squared cosine of omega t plus theta is equal to negative 1 over LC a cosine of omega t plus theta. All I did was just plug in VC and its second derivative into the equation. And then we can just cancel everything out. So we can cancel the cosines out, and we can cancel the a's out. And we end up with negative omega squared is equal to negative 1 over LC. So this tells us that omega is equal to the square root of 1 over LC. Since omega squared is equal to 1 over LC. And you could take the positive or the negative case, like the answer in the end is going to be the same. So that's that. And then we need to do a couple more steps now. So we figured out what omega is, but we also need to figure out what A and theta are. So any ideas on what to do now? Need more information. So what should we do?
Conditions.
Yeah, let's try out the initial conditions. So VC and IL. So let's try plugging in VC of 0 into A cosine of 0 times t plus theta, which means A cosine of theta is equal to 1. And we still need more information since we have two variables but only one equation. So let's use the second initial condition. And as a general piece of advice, if you have an nth order differential equation, as we do here, we're going to need n initial conditions. So because we have a second order differential equation here, we're going to need two initial conditions in order to solve it. So in order to do this, we're going to need to somehow write VC in the form of IL, right? So the way we're going to do this is we're going to take the derivative. We already know what its derivative is. And
So we had the equation we did in part A,
did in part A.
where you said that dVC dt was negative IL over C.
Exactly, yeah. And that's what I was trying to get at as well. So we're going to use the fact that dVC dt is equal to minus IL over C. That's essentially the idea. So this is going to be equal to IC over C, which is then equal to minus IL over C. So then this tells us that dVC dt of 0 is going to be equal to minus IL of 0. And if we plug it in, well, dVC dt of 0 is going to be equal to minus a 1 over the square root of LC times, let's see, sine of theta is going to be equal to negative IL of 0, which is 0 over C. So that's still equal to 0. And if we divide by 1 over square root of LC on both sides, this tells us that A sine of theta is equal to 0. So we have two equations now. A cosine of theta is equal to 1. A sine of theta is equal to 0. And we can essentially solve this. And to do this, we can break it up into two cases where A is equal to 0 and sine of theta is equal to 0. And if you try to assume A equals 0, notice that here you're going to get 0 is equal to 1. So it's a contradiction. So this is not possible. So this tells us that sine of theta has to be equal to 0, meaning theta is equal to 0 or pi. And again, we're going to have two cases, but both of them are going to lead to the same solution. Because if theta is equal to 0, A is going to be equal to 0 since cosine of theta is 1. So A times 1 is equal to 1. So A is equal to 1, cosine of theta is equal to 0. Or the other solution is like A is equal to -1 and cosine of theta is equal to, or sorry, theta is equal to pi. And those two solutions will be the exact same because VC is equal to cosine of omega t. I know there's like a lot going on, but any questions about what happened?
Why are the two solutions the same again? I would imagine that if cosine of pi is equal to 0, then, or sorry, if you plug in pi, A cosine pi, cosine
So
pi would be -1 and A would be -1, not 1?
A would be -1 and theta would be pi, right? As I kind of wrote here. But then these two expressions are equivalent due to like trigonometric identities. If you take cosine of x plus pi, that's equal to negative cosine of x.
Oh, okay. Yeah.
Yeah. So these two are equal. Yeah, that was a good question. And we solve for VC. We could do the exact same guess and check process to solve for IL, but I think a smarter way to solve for IL is just to realize that IL is equal to C dvc dt. So in other words, IL is equal to minus C dvc dt. So if we took the derivative of that, I'm running out of space here, but you could show that VC is cosine of omega t, and IL is equal to minus, so you have a double negative, but you have minus C negative sine of omega t. So then you're going to get omega c sine of omega t. And if you plug in all the numbers, it's going to be something like this. So it's going to be c over the square root of LC sine of 1 over LCT. And similarly, we're going to have cosine of 1 over LCT.
Sorry, how could you explain again how we got B?
How we got V?
B for the IL equation.
Yeah, so instead of doing the whole guess and check process, we could realize that IL is just negative C dvc dt from part A, I guess, right?
Okay.
And then we can just plug in what we already know for VC of t into the derivative. So yeah. And if we were to graph these solutions, I think this is where the key insight comes in. This is the graph of a cosine. So this is the graph of VC. You'll notice that excuse my horrible drawing skills, but they're exactly like out of phase. In other words, when the capacitor is fully charged, the inductor has 0 flux. remember that flux is equal to Li. So if I is equal to 0, then flux is equal to 0. And when the capacitor is uncharged, in other words, the voltage across the capacitor is 0, the inductor has maximum flux. In other words, all the flux is in the inductor. So you'll notice that like the two are just like swapping places each time. And that the voltages and currents are all sinusoidal. So any questions about that? All right, if we don't have any questions about that, I think I'm gonna do a brief discussion about the energy and then talk about what you need to do to solve for the remaining parts of the discussion. So the energy across a capacitor is given as 1/2 CV squared, whereas the energy in the inductor is given as 1/2 Li squared. And since we know that Vc is equal to cosine of 1 over LCT, and IL is equal to, what was it again? C over the square root of LC. Sine of 1 over the square root of LCT. We can just take a look at their individual energies. So this would be 1/2 C times cosine squared. And the energy across the inductor would be 1/2 L times C squared over LC sine squared of 1 over LCT. And this tells us that the total energy in our circuit is the sum of the two, which if you actually do the math, you'll notice that the energy across the inductor is 1/2 C sine squared of 1 over LCT. So since cosine squared plus sine squared is equal to 1, the amount of energy in the inductor is going to remain constant, which is quite amazing actually. The energy is constant, and really what's happening is it's just going back and forth between these two devices. So that's like the key insight that you want to get out of this problem.
Sorry, that is 1/2 C, which is the capacitor value, not just a constant number.
1/2 C, this is the capacitance.
Okay, thank you.
Yeah. The units are kind of weird here. Like, I think somewhere, if you actually do the dimensional analysis, it'll all work out the way it does. But like,
So
I guess because yeah,
does the total energy not rely on the voltage?
exactly, yeah. So the total energy doesn't rely on, it only relies on the initial voltage. So here, remember that V initial or V0 was equal to 1.
So if it was like 2, then it would be just C.
It'd be C, I think Vs squared.
Okay, thank you.
Yeah. And that's because Vc would be equal to like Vs cosine of 1 over LCT. Okay, and then I know it's 12:02, so I'll wrap up real quick, but part E and F are just getting you to solve the differential equation using diagonalization. So I think all you need to do here is take the guess and check approach. You'll realize that like the eigenvalues are complex. And I think the idea here that I want to get at is that if you have a linear combination of complex exponentials, you might remember from the previous discussion from Euler's formula that the sum of these two complex exponentials that are like conjugates of each other. So if you have e to the j something and e to the minus j the same thing, this is going to be equal to like cosine of something. So the answer here is going to match the answer you got in part B with all the guess and check here. So part E and F are really all there just for you to verify your guess and check works. What about the charge? The charge of the, I guess, like entire circuit. So like Q equals CV. I think you can show here that since the graph of VC is sinusoidal like this, and Q is equal to CV, it'll just be a scaled multiple of this graph. So the charge will be sinusoidal, and the current will also be sinusoidal, and the flux will also be sinusoidal. But the energy in the entire circuit is constant. Okay. And I think that is all I have to say for today. So if you have any questions, feel free to stick around and ask. And if not, thank you all for coming.